Welcome to section 5.1. In chapter 5, we're going to be discussing inverse functions. In this section, our title is Finding the Inverse, Numerical, Graphic, and Symbolic Approaches. So before we get into finding the inverse, we need to determine what exactly the inverse is. Well, so far we've had a lot of functions that take an x value and evaluate that x value and return a y value. Okay, so here we would take f of 1, for instance, plug that into our function, and get our y value. So the x value gives us the y value. Now, the inverse function is going to undo whatever our function does. So, for instance, we would like to find a function that takes this y value as its input and turns it back into the x value as the output. So, the notation for the inverse function, which is given in the notes for this section, we would say that given this function f, its inverse is denoted as f inverse of x. Now the inverse function does not exist in a vacuum. This function f inverse would be related to this function f that we started with. Particularly, it is the function that undoes everything that the function f does. So if f takes in 1 and gives us back 1, f inverse will take in the 1 that we got and turn it back into the 1 we started with. Another example, if f takes in 2, we would get 2 times 2 minus 1, that's 4 minus 1, that's 3. So f inverse would take in 3 and give us back the 2 that we started with. Now, it may not be clear exactly how it's going to do that, but that is what the inverse function should do. If f of 3 is 2 times 3 minus 1, that would be 5, then f inverse of 5 would give us back 3. That's all that we know about the inverse function. It undoes whatever the function that it's related to does. So the first thing that we can do, given a function, in this case we'll define our function using a table, is to figure out the inverse relationship. So this function takes in 1 and gives us 2, which means that our inverse function will take in 2 and give us back 1. Similarly, our original function takes 2, gives us back 3, so our inverse will take 3 and give us back 2. And we can continue in this fashion. Our original function has 3 as an input and returns 5, so our inverse will take that 5 and turn it back into a 3 for us. And so on. Alright, so suppose we have another function defined here. Let's find the inverse relationship for this. So we'll have x and the inverse down below. Alright, well, we know that all of our outputs are going to turn into inputs. That's what our inverse does. It takes the outputs and turns them into something else. So 2, 2, 4, 6, 2. Well, here we see that when we input 1 into our function, we get 2. So when we input 2, we should get 1. Similarly, when we input 2, we get 2 back. So when we plug in 2, we should get 2 back. When we plug in 3, we get 4. So when we plug 4 into the inverse, we should get back to 3. 5 goes to 6 on the original function, so 6 will go back to 5. And here 7 gave us 2, so we're plugging that 2 in to try to get 7 back. Now this example illustrates the danger with the inverses. Thinking back to chapter 1, remember that each input has to give us a unique output. But here we have 2 outputting 1, 2 outputting 2, and 2 outputting 7. So this thing is not a function. Alright, so why is this happening in this case? Well, it's because we had all of these repeating 2's as outputs in the original function. So if this happens, if we have a bunch of copies of outputs, then when we go to find the inverse, it's not going to be a function. And that brings us to our first important definition in this chapter. So on the first page of the notes for this section, near the bottom, or near the middle bottom, you'll see the definition of one-to-one functions. And that says that a function is one-to-one if whenever we have different inputs, we get different outputs. So here I have x equals 1 and x equals 2. They're both giving me the output y equals 2. Moreover, when x equals 7, we see that y equals 2. So what this means is that this function is not one-to-one. Different outputs, or different inputs, are not necessarily giving us different outputs. We have repeating outputs. So this function is not 1 to 1, and that is why its inverse relationship is not a function. So that's what we need to watch out for in this section. If we're interested in finding the inverse function of a function, we need to begin by making sure the function that we start with is one-to-one. In other words, when we're all done with this, that we don't get some relationship that isn't even a function. That wouldn't be very useful. Now, another way of viewing the original function that we started with, there in the second example that we just looked at, would be graphically. So if I were to plot the points that we saw on the graph, 1, 2 would be right there, 2, 2 would be right next to it on the same horizontal line, 3, 4 be up here, 5, 6, that should be over 1, 5, 6, and 7, 2. Okay. So here we can see our primary tool that we're going to use for determining if a function is one-to-one is what we call the horizontal line test. So this is the graph of the function that we discussed, but looking at it, it is a function, right? We can use the vertical line test. Our vertical lines never hit this function at more than 1 point, so this is a function. But a horizontal line here at a height of 2 hits 1, 2, 3 different points. So this tells us that it is not one-to-one. This is the abbreviation I like to use for one-to-one. The test that we're using is at the bottom of that first page of the notes, Theorem 5.1, the horizontal line test. So just like the vertical line test, we flip this on its side. If any horizontal line hits our graph at more than 1 point, then it is not one-to-one. And as we just saw, this implies that it is not invertible. And by invertible, I mean the inverse relationship is not a function. So that is our primary starting point in this section. Whenever we want to find an inverse, we first have to make sure that the inverse function will exist. And that's never going to happen for a function that is not one-to-one. So to see an example of a one-to-one function, we'll go back to that first table that we looked at. 1, 2 right there. 2, 3 right above it. 3, 5. 5, 9. And 9, 21, way up here. So we can see on this graph, every horizontal line that we draw hits the graph at most 1 point. So this function is one-to-one, and therefore its inverse, the inverse relationship, when we flip all of our points and go backwards from y to x, is a function. And we could find that function. In fact, we did find that function. Going back to the previous page, we see the inverse relationship. So let's take a look at a couple more examples of one-to-oneness. So suppose we have our first example here, f of x equals the absolute value of x plus 2. Well, I'll do this one first without a calculator and then show you how you would handle it with a calculator. Remember, our absolute value function is v-shaped, and plus 2 means we're going to shift it up 2 units so we can get a rough sketch of the graph of this. Well, there's the graph of our function, and we can see if we pass a horizontal line over it in a lot of different places, it's going to hit the graph at more than 1 point. So what does that mean in terms of a table? Well, if we plug in, say, x equals 1, we would get 1 in absolute values plus 2. So we would get y equals 3 as the output. Similarly, if we plug in x equals -1, the absolute value of -1 plus 2, that's 1 plus 2, so we get 3 again. So we have different x values giving us the same y values. Alright, so horizontal line test to test if this is one-to-one. Since we hit at more than 1 point, this is not one-to-one. Here we see a second function that we would like to analyze, x plus 1 quantity cubed. Now, this function we can graph pretty easily. The function x cubed rises like that. Now, x plus 1 inside means we're going to shift to the left 1 unit. So the actual graph of our function, shift to the left 1 unit, is going to look something like that. Alright, well, we can pass a horizontal line over this thing anywhere we like, and we see that it only ever hits the graph at 1 point. So this is a one-to-one function. Which means it's invertible, and later on we will in fact be able to find the inverse of this function. So that one was one-to-one. It passed the horizontal line test, we might say. Every horizontal line we could imagine hits the graph at most 1 point. We don't have any duplicates. Now, before I move on, I would like to look at the graphs of these in the calculator. If you're ever stuck and you don't remember what the graph looks like, you can always toss that function into your calculator and apply the horizontal line test in there. Alright, so if we start with our first function, f of x equals absolute value of x plus 2. We'll plug that into our y equals screen and hit enter. Now you want to make sure you can see a fair amount of the graph, so you might use a standard zoom or zoom out a little bit. We can extrapolate, and we know that the graph is V-shaped basically forever. So we can see right away, if we hold a horizontal line up across our graph, say at a height of 3 or 4, or anywhere above that sort of vertex, that y-intercept where the v's point lies, that this is going to fail the horizontal line test. A horizontal line will hit the graph at more than one point and therefore make it not one-to-one and not invertible. Then if we go back and we plug in our second function, g of x equals x plus 1 quantity cubed, and hit enter. Alright, now our graph is replaced by something similar to what we graphed by hand, and we can again apply the horizontal line test and see that this function is in fact one-to-one. Every horizontal line that you hold, and then you can use the edge of your hand, or you can hold up a sheet of paper and move up the entirety of the graph and make sure that you're only intersecting the graph at one point at most. So this one we can determine is one-to-one. Alright, so that's our approach. Before we jump into finding the inverse, we want to make sure that an inverse will be found, that it is possible to find the inverse function. Now, symbolically what the inverse does, if we think about our function f, taking x values from its domain, say here we have some x value in the set of inputs that f is allowed to take in, and we'll send that, use f to evaluate that, and find a y value associated with it. Alright, now that y value is going to be in the range of f. Okay, and so far that's all that we've done. We've taken in x values, had our function do some work, and found y values associated with that x value. Well, now the inverse function hunts around in the bin of outputs, and maybe it'll take this particular output, y, and turn it back into x. That is to say that f inverse takes its inputs from the range of f, making it the domain of f inverse. And then our f inverse takes those values and turns them into values from the domain of f, making the domain of f the range of f inverse. Alright, symbolically, how does that look? Well, f takes x as its input and turns it into y. Then f inverse takes that number as its input and turns it back into x for us. And that's true for every x in the domain of the function that we start with, and it's true for every y in the range of the function that we start with. So there's a convenient takeaway from this way of thinking about the inverse. By the definition of the inverse function, we see that the domain of the function is going to be equal to or equivalent to the range of the inverse, if it exists. And similarly, the range of the function is equal to the domain of the inverse. Right? The domain of f is where we should get back to using our inverse function. That should be the outputs of the inverse function. And similarly, the range of f, the things that f produces, are the things that we're allowed to plug into the inverse. So that's kind of a nice result. And that is something that's going to be a little bit important later on when we look at functions that have interesting domains and ranges. So returning to the original example that we looked at here, we would see that the domain of f, and I'll call it capital D with a subscript f, is the set of numbers 1, 2, 3, 5, and 9, while the range of f is the numbers 2, 3, 5, 9, and 21. Now when we invert, when we turn all of our x values into y values and our y values into the x values that they came from, we see that the domain of f inverse is 2, 3, 5, 9, and 21. And the range of f inverse is the outputs 1, 2, 3, 5, and 9. So that's a connection. The domain of the function and the range of the inverse are, by definition, going to be identical. Similarly, the range of the function and the domain of the inverse are going to be identical by virtue of what the inverse function does and what it is. Now, this way of thinking of the domain and the range, and the function and its inverse, gives us the algebraic approach that we're going to use to find inverses symbolically. If we're given a symbolic representation of a function, how would we find the inverse? Well, our function takes inputs and returns outputs. The inverse takes outputs in as inputs and returns those inputs that we started from as its outputs. So the inverse function swaps x's and y's, essentially. The old y values become the x values, in our way of thinking of things, and the x values now become the outputs, or the y values. So if you're looking at the notes on the next page, you'll see the procedure for finding the inverse function. So the first thing that we do is determine whether the function is invertible. If it's not, then this is not going to work, and we might as well stop now. So if the function is 1-to-1, if the function that we are starting with is invertible, the first thing that we'll do is rename things. Alright, so here we have our function, f of x. We would like to find f inverse. So the first thing that we want to do is determine if the inverse function will exist. In other words, determine if this function that we're looking at is 1-to-1. Now this one's very easy to graph. We've been doing this from the beginning. This is a line with a y-intercept at -1 and a slope of 2. So we can rise 2 and run 1. And we see that this function never doubles back on itself, and any horizontal line that we might be interested in is going to intersect our graph at only one point. So this is 1-to-1, which means we should proceed. So we replace f of x with y. Alright, now what the inverse will do is invert everything. In other words, our x's become our y's and our y's become our x's. So symbolically, we do that. We replace our x's with our y's and our y's with our x's. So now we're talking about the inverse relationship. Alright, we've inverted, we're now in inverse land. And finally, we need to solve for y because we would like to write this in function notation. So, I'll maybe add 1 to both sides. And then I'll divide both sides by 2 to get y by itself, so x plus 1 over 2 equals y. Now this y is our inverse function, so we rename it as such. And that is our inverse function. So let's see what that looks like if we graph it. Well, another way of writing this would be x over 2 plus 1 over 2, or 1/2 x plus 1/2. Now it's a little easier to see in those terms. Here we have our slope and our y-intercept. So if we come up and let's go ahead and graph our original function while we're at it so we can see how these compare to each other. So we've got -1, 1. There we go. So there's our original. And I'll graph this as a dotted line. Our inverse has a y-intercept at 1/2 and contains the point, let's see, we would rise 1 and run 2. So if we rise 1, we'll be up at 3/2 and run 2. There is our inverse function. Now, if I go in the other direction, if I fall 1 and run -2, we could go down to -1/2 and back 2 units. My line's a little bit lumpy, but we can kind of see what we're working with right there. Now, I recommend, especially in this section, that you use graph paper for any graphing type questions. The idea being that there is a relationship between the graphs that we're seeing. Alright, so I want to look at the tables that we come up with for these functions. So our original function, f of x, if we plug 0 in, we would get 2 times 0 minus 1, -1. That's our y-intercept, we knew that from the beginning. If we plug in 1, we'll get 2 times 1 minus 1, so that's 2 minus 1. If we plug in 2, we get 4 minus 1. Plug in 3, we'll get 6 minus 1. Plug in 4, we'll get 8 minus 1, and so on. If we go in the negative direction, -2 minus 1 would be -3. -4 minus 1, -5. -6 minus 1 would give us -7, and so on. Okay. Well, on the graph of our inverse, we have x. Since this is our inverse function, if we plug in -1, let's see what we get. Well, -1 plus 1 would be 0 over 2, which gives us 0. If we plug in +1, what do we get? Well, +1 plus 1 over 2 would be 2 over 2, which is 1. If we plug in 3, now what's the connection? I'm plugging in the old outputs. So 3 plus 1 over 2, that would be 4 over 2, which is 2. 5 plus 1 over 2, that's 6 over 2, that's 3. And 7 over 2, or 7 plus 1 rather, over 2. 8 over 2 gives us 4. And we can go in the other direction. If we plugged in -3, we would get -1 back out. You can verify that. -5 would give us -2. -7 would give us -3. -9 would give us -4. Alright. Now the relationship between these points, -4, -9, and -9, -4, can be seen graphically. So if we look at these 2 points, 0, -1, our original y-intercept, and -1, 0. Alright. How about negative 1, negative 3? Let's see, negative 1, negative 3 right there. And negative 3, negative 1. My line's a little bit crooked. Negative 3, negative 1 should be right about there. Alright. The relationship between all of these pairs of points, these sort of associated points, is that they lie on opposite sides, of the diagonal line y equals x. So there's our original function, and we have our inverse right there. And if you turn your page sideways so that y equals x is vertical, you'll see that these look like mirror images of each other. We can do the same kind of thing in the grapher when we get to that. So if we plug our two functions in, if we plug in 2x minus 1 and the inverse function that we found, x plus 1 over 2, and we hit graph, we'll see the two lines graphing there. Now, if you're using a standard window, it might be a little bit hard to see this relationship. So if you take your calculator and turn it 45 degrees to the left, these aren't really going to look like twins. They aren't going to look like mirror images of each other. But if you zoom square, so right next to standard zoom, you have a square zoom. That's going to take your zoom and make it square. In other words, it's going to fix it so that your X tick marks and your Y tick marks are equally spaced, or are identically spaced. Now if you turn your graph 45 degrees to the left so that Y equals X is vertical, and you might want to graph Y equals X while you're at it, now these two graphs look very similar to each other. So we'll look at more of that type of thing in class, but that is the graphical relationship between a function and its inverse. They look like mirror images across or about y equals x, so there's this new type of symmetry that we can observe. Alright, so here we have another of this same type of question. We're going to find g inverse given the function g as a starting point. Well, we already saw that this function is one-to-one, so we can begin by replacing g of x with y. So we'll call it y equals x plus 1 quantity cubed. Alright, so that's our first step. Second step, we are going to swap out our x's and y's. Turn this into x equals y plus 1 quantity cubed. Alright. Now the third step, solve the new equation for y. Now we're talking about the inverse relationship. But this is usually the trickiest part of the process. We have to solve for y, and right now y is stuck inside of an expression that's being cubed. So in terms of the process of solving for y, there's no one way to go about it. We need to use any tool at our disposal, anything that we know so far about solving equations for a given variable. Alright, so in this case, I think that if we cube root both sides, we'll get the cube root of x and the cube root of y plus 1 quantity cubed. And those two actions cancel each other out. So the cube root of x equals y plus 1. And we're almost done. We can just subtract 1 from both sides. So the cube root of x minus 1 equals y. And now we're done. This y is our inverse function, so we'll rename it. And we will call it, in this case, g inverse of x. And that's our inverse function. Alright, so I'll go to the graphing calculator again. I will plug in both the original function that we started with and our inverse, and sort of look at what those two graphs look like in relation to each other. Alright, so here we'll plug in x plus 1 quantity cubed, and below it we'll plug in the cube root of x under the math menu, minus 1 on the outside. Now if you've got your calculator handy, I might plug in y equals x as well. So y equals x is going to be sort of a visual aid to see if we did everything right. So far, this graphical approach is really the only way that we have to verify that we did the work correctly. So if we look at the two graphs and they look like inverses, if they're symmetric about that diagonal line y equals x, then chances are that we're okay and that our inverse function is correct. So plugging those both in and looking at it, if you turn it 45 degrees so that y equals x is vertical, I think these sure do look like inverse functions. Right here, going from the bottom right area up to the upper left area, you would see the original function. And going from the bottom left to the upper right, this is if your graph is turned, if you've angled your calculator, you'll see our inverse function. And they're nicely symmetrical. They look kind of like a vase, in my opinion. Alright, so that's our procedure. Now, let's try one more. Alright, so we would like to find h inverse, given that h of x is this function x squared minus 1. So the first thing we want to do is figure out, is this 1-to-1? Well, we know what x squared minus 1 looks like. That's the basic parabola shifted down 1 unit. And that fails the horizontal line test. So this is not 1-to-1. And therefore, no inverse function exists. So going back to our previous example, if we think of the graph of the inverse as being the original graph rotated across y equals x, we can see how that would work with our quadratic here. So if we have this parabola, or something kind of like a parabola, and the line y equals x, if we flip this parabola across that line, if you take the top half and rotate it across, you'll end up with something like this. So turning those sideways, these are symmetrically mirrored across y equals x. But this thing, the inverse relation, is not a function. And so that's why we can call it quits right there. No inverse function exists, so we don't have to try to find it. Alright. Now, if we're given a table, as we are in this example, we don't necessarily need to find the inverse function, the whole thing, in order to evaluate the inverse at certain values. So if I know, for instance, that f of 1 is negative 1, f of 4 is negative 2, f of negative 2 is 6, and so on, then I know that f inverse of the output is going to take me back to the input. So f inverse of 6, I'll look for 6 as an output, and I'll see what would that go back to, negative 2. F inverse of 11, so I'll look for 11 in the output pile. And what does that go back to? It goes back to 11. Now our third example here is a little bit tricky. I want to figure out what f inverse of f of 4 is. Well, first I need to know what f of 4 is before I can start evaluating the inverse at whatever that is. So note that f of 4, going from x's to y's now, is negative 2. So we'll plug that in, say what we're actually trying to find is f inverse of negative 2. So in that case, we're going to look, this is sort of like a y value, this is an output, but we're going to use it as an input into the inverse. Negative 2 goes back to 4. So our thought process there, f inverse of f of 4, kind of like the order of operations, we work our way outwards. So the innermost parentheses, I have a 4. The parentheses outside of that ask me to plug 4 into the function f, which gives me negative 2 as the result. And then I have to figure out what is f inverse of negative 2, and for that I look in the output pile. So f inverse of negative 2 came from 4, so it'll go back to 4. Alright. I'd like to look at one more finding the inverse type question. So here we've got a function, f of x equals negative square root of x plus 1. We're going to find its inverse, assuming that inverse exists. So the first thing to do would be to graph f of x and see if it's 1 to 1. Well, we're going to flip vertically, and we're going to shift to the left 1 unit. So our square root function will flip vertically and shift to the left 1 unit. So something along these lines is what we're dealing with. Now this function is decreasing forever. It never has any local maxes or mins, which means any horizontal lines that we trace across it are going to hit at one point only. So this is 1 to 1. So let's change y, or change f of x to y. And let's swap everything. And now we'll try to solve for y. Well, if I isolate the radical, I have a radical equation, that's what I'm trying to solve. So if I move the negative over to the other side by multiplying both sides by negative 1, negative x equals the square root of y plus 1. I can then square both sides, canceling the radical, and get negative x squared equals y plus 1. If I subtract 1 from both sides, I get y equals negative x squared minus 1. Now it's worth noting, if we square negative x, remember back from our discussion of even and odd functions, we're just going to get x squared. So that's our inverse function. Alright, so let's graph both of those. If we plug our original function and our supposed inverse into the grapher, negative square root of x plus 1, and down below it, x squared minus 1. Let's hit the graph button. Alright. Now these certainly seem similar to each other, but I would argue if you turn your calculator 45 degrees to the left, that the square root function and the square function, the quadratic, the parabola, don't look exactly like mirror images of each other. Now the reason for that is that the domain of our original function is what? Well, if we look at the graph, it starts at negative 1 and goes up from there. On the other hand, the range of our original function, notice that the highest point on our graph is 0. So we go from negative infinity up to 0 vertically. And that is supposed to match the domain of the inverse. But the domain of the inverse function, looking at this function, is all real numbers. So what we need to do, and similarly our range of the inverse function should match the domain of the original. Well, in that part we're okay. The range of f inverse is already -1 to infinity. So the only thing that we need to do is say f inverse of x is defined to be x squared minus 1, where x is less than or equal to 0. In other words, we need to express this restriction on the domain in the definition of the inverse function that we are supplying. So this restriction on the domain, saying that x has to be negative, or non-positive I should say, that is a requirement because the range of our original function had a restriction. So this is really our inverse. Our inverse is the function's symbolic definition and covering our bases with this caveat about the domain of that function. So by default, this function doesn't have a domain restriction. It needs a domain restriction in order to accomplish this requirement for the domain of that inverse function to match the range of the original function. I have one additional note to make about testing whether a function is one-to-one. By virtue of the horizontal line test, we can find an analogy, a sort of theorem of algebra, that says that a function is one-to-one if and only if its graph either always increases, so it's always rising, never doubles back on itself, or if it's always decreasing. So we can decrease quickly or slowly or some combination thereof. And we see that the horizontal lines only hit this graph at one point. Trouble arises if we have a graph that increases and then decreases and then increases, maybe. So there we have issues. In other words, if our function has any local maxima or minima, we might be in trouble. So a function that's always increasing, something like the square root of x, is one-to-one. A function that's always decreasing, for instance the one that we just looked at, the negative square root of x plus 1, this function is always decreasing. As we read from left to right, it's getting smaller, and both of these are one-to-one. So that's another sort of version of the horizontal line test that I kind of like. It saves a little bit of time when you know that the function you're dealing with, for instance, a square root function, a cube root function, a cubic function, something like that, is always exhibiting one or the other of these behaviors. It's always increasing or always decreasing. Then we can conclude very quickly that our functions are one-to-one. Alright, so that is section 5.1. Go ahead and get started on those homework problems and bring any questions to class.